Good morning. Last class, we derived an expression for the ideal change in free entropy of an ideal free energy of an ideal solution. And the reason I was tongue-tied is because the only component of it was the entropy. So an ideal solution assumes that all the molecules of the two components 1 and 2 are the same size when you mix them together. And it also assumes that there is no difference in the intermolecular forces between molecules of 1 interacting with 1, 2 interacting with 2, and 1 interacting with 2. So that when you exchange the nearest neighbors for one or the other, there's no change in enthalpy. So we're not saying the enthalpy was 0. There still are intermolecular forces, but we were saying that they were the same for 1 and 1 and 1 and 2. So today we're going to introduce two changes, two developments to this analysis. So we'll go from two solvent type species where each molecule occupies a single site on this hypothetical lattice to one in which one of the components, that is component number 2, will be a polymer, and that will introduce a slight change to our entropy of mixing, which will actually have quite profound results. But it will only have profound results because we're also introducing the idea that the intermolecular forces between 1 and 1 and 2 and 2 are different. And because the interaction energies between 1 and 1 and 2 and 2 might be favorable, the one with the more favorable intermolecular force might want to exclude the other component from the mixture. And that will be the basis of phase separation in polymer solutions, and also the reason why polymers become less soluble as the molecular weight increases, and ultimately, which we'll cover on Wednesday and Friday, why two polymer chains together, two solutions of two different polymers, so two polymers melted together, no solvent, don't want to mix at all in general, unless they're very similar chemically, or have complementary molecular structures. Okay, so when we go from the ideal free energy of mixing to a polymer and a solvent along with unequal intermolecular forces, we go from the ideal to a regular solution. So ideal solution to regular solution, and this is attributed in the case of polymers to Flory and Huggins. So this is the Flory Huggins theory. Flory and Huggins developed this independently. And we're going to start with the entropy term. And after we're done with the entropy, we'll talk about what happens to the enthalpy. So the Flory Huggins theory, entropy of mixing. And what we're going to, how we're going to set this up is that we have a polymer chain with R covalently bonded segments. This is just a model, right? This is just a model on some checkerboard or chessboard. So R is really, in real life, equivalent to something we had been calling X. But I'm going to call it R because I don't want to assume too much of this mathematical model. This is really just a model. So this is really like it's sort of like the degree of polymerization, but with dots on a checkerboard. So we have R covalently bonded segments, and we're going to assume that the segment size equals the solvent size. And this gives us a relation for R equals V2 over V1, which is the molar volume of the polymer chain over the molar volume of the solvent. And what we are going to do is to move the polymer chains that are immobilized into a new lattice, so from a lattice of just pure polymer chains to a new lattice that comprises the number of segments of all the polymer chains plus all the lattice sites as a result of adding the solvent in. So we're going to move the polymer from immobilized state into solution. Into solution or lattice of the total number of sites n naught equals n1 plus r n2 sites. This is the total size of the lattice, where n1 is the number of solvent molecules and N2 is the number of polymer molecules. We're going to make a lot of assumptions today because we're just talking about a checkerboard with checkers on them. We're assuming monodispersity here, that they all have the same length R. What we are going to do is we're going to talk in terms of volume fraction instead of mole fraction. So in the end, what we're going to get is an expression for the entropy of mixing that basically just swaps out the volume fraction, or sorry, swaps out the mole fractions from the ideal solution with the volume fractions in Flory Huggins theory. So what's the definition of volume fraction? The reason we do this is because we don't necessarily know the moles, but it's easy to measure the volumes because we just know the volumes of the stuff that we dump into the mix. So yeah.
Are we talking about a single polymer molecule? Because I notice we have Rn2.
No, we're talking about there can be more than one. This could be anything. So we're going to switch in the ideal solution case from talking about mole fraction to volume fraction phi sub I. And the expressions for volume fraction for the solvent and the polymer, for the solvent is just N1 over N1 plus R N2. So this is just the number of solvent molecules, the number of sites occupied by solvent molecules divided by the total size of the lattice. So that would be the volume fraction. And for phi 2, we have Rn2 over N1 plus Rn2, where this is the length of the chain times the number of chains. So that's the total number of sites occupied by polymer molecules divided by, again, the total size of the lattice. Okay. How do we get the change in entropy upon mixing? So this argument is called the quick route, or route, depending on where you grew up, in the textbook. And it relies on a little bit of imagination, but bear with me. So say that in the pure polymer phase and in the pure polymer phase and in the mixed phase, we have the same degrees of conformational entropy. So the polymer chains, this is a huge assumption and it's wrong, but it helps us get to the right, it helps us develop an intuition for how polymer chains mix with solvents and each other. So you're assuming that the number of well, I'm waving my arms because I'm a polymer chain. Assuming that the number of conformations is the same in the pure phase as in the solvent phase. Now really it's going to depend on what the solvent is, because it might go like this, but we're going to assume that it's just like this, like wacky, wavy, inflatable arm flailing tube man. So, okay. As a result, the change in entropy is really just the difference in the number of sites on the lattice where you can put the polymer chain's center of mass, because we're going to assume that the conformational freedom is the same in both the pure phase and the mixed phase. So really all we need to do is calculate the difference in the number of sites available for the center of mass to sit. So this is called, this is the Flory Huggins entropy of mixing, and this is the quick root in your textbook. The quick root in your textbook is followed by the long root. We're not going to do that. So what we're going to do is assume they both give you the same answer, and you're not responsible for either derivation. So we'll get to the answer. So we're going to assume that the polymer chain has the same conformational degrees of freedom in pure phase and mixed phase. So the change in entropy upon mixing is the increased number of sites in which the center of mass of the polymer chain can sit. In which the polymer center of mass can sit. So the number of possible locations of the center of mass in the pure polymer phase is the size of the lattice occupied by just the pure polymer phase before mixing, and the number of possible locations of the center of mass in the mixed phase is N1 plus R N2, the total size of the lattice. Yeah.
What does R refer to again?
R is the length of the polymer chain in our mathematical model. So it's a number of adjacent sites occupied by polymer monomers. Okay, so considering only the change in entropy from the perspective of one polymer molecule going from the pure phase to the mixed phase is K natural log N1 plus R N2 minus K natural log R N2. And by our definition of phi, the volume fraction, this is negative K natural log phi 2. Now we can make the same argument for the center of mass of the solvent molecules. And what we get for delta S1 of mixing is minus K natural log phi 1. So to get the total entropy of mixing for the solution, we just add up the change in entropy for each component and then multiply it by the number of molecules in the system or the number of moles in the system. So for the whole system, we multiply each term by the number of molecules of each type. So the total entropy of mixing is minus K N1 natural log phi 1 plus N2 natural log phi 2. Now this is very similar to the entropy of mixing of the ideal solution, except that we've replaced the x sub 1s and the x sub 2s with phi sub 1s and phi sub 2s. So a lot of verbiage and chalk dust spilled just to get pretty much the same result. But what is encapsulated in the volume fraction and the number of polymer chains is that for large degrees of polymerization, or large R, which is equivalent to large degrees of polymerization in a real system, not just this mathematical construction, this term gets very small. So it becomes smaller with large R because phi approaches 1, and also the number of polymer chains decreases. So then you have only the entropy of mixing due to the solvent that's contributing to the favorable entropy of mixing of the entire mixture. So just by increasing the length of the polymer chain, you make it less soluble, you make it less favorable to mix. we can recover the ideal solution. So the ideal solution is a special case of Flory Huggins in the case where instead of a polymer, we just have monomers. So R equals 1, and then phi1 is x1, and phi2 is x2. And if we make these substitutions, we just get the ideal solution theory. Okay, now we need to take this, because this is just one part of the free energy that predicts the equilibrium phase behavior of a polymer-solvent mixture. This is just the delta S term. Now what about delta H? So delta H of mixing is no longer going to be 0, because we're going to say that the two different monomers or solvents, the argument works for different solvents as well as for polymers, do not have the same intermolecular forces and therefore don't have the same delta H. So what is the enthalpy of mixing? The enthalpy of mixing is unequal intermolecular forces. So we're going to start with delta H of mixing equals the change in internal energy upon mixing plus pressure times the change in volume upon mixing. Now, in chemical systems where we're just mixing stuff, there's usually a negligible change in volume. Incidentally, I think it's ethanol and water you mix together, the volume actually goes down. But we're going to forget that. The lattice is exactly the same size. So what I told you in last class is true. Is true for this model. The change in internal energy is just a change in the intermolecular forces, which manifests directly as the change in enthalpy from the unmixed states to the mixed states. So what do we know? Are these forces attractive or repulsive? They're generally going to be attractive. It's all uncharged molecules pairwise attract We're not going to worry about multi-body systems for now. Just consider adjacent molecules in adjacent sites in a hypothetical lattice or in a solution. There are going to be favorable intermolecular forces between them. And how do they attract? They attract by van der Waals force. Van der Waals forces. And the van der Waals forces are three things. They're the dipole-dipole force, where you need two permanent dipoles that interact with each other. Molecules that don't have permanent dipoles can't interact this way. You have dipole-induced dipole. Forces, which you can have a permanent dipole that's interacting with the electron cloud of an adjacent molecule that polarizes, that shifts the electron cloud a little bit away from its equilibrium position, creating a new dipole, which the permanent dipole then interacts with in an attractive way. And then you have London dispersion forces. Yeah.
Just to clarify, we always hear about hydrogen bonding as a strong van der Waals force, but that's just a special case of dipole-dipole, correct?
Hydrogen bonding is an especially strong case of the dipole-dipole force. Usually when we're talking about van der Waals forces in common parlance, we would kind of put hydrogen bonding in its own category because it's so strong. But strictly speaking, it's a dipole-dipole force. Okay. These together, interestingly, if you take my class NANO 202, Seng 212 in the fall, which you're all welcome to do, we'll go through these what these things do in detail and how they manifest in macroscopic bodies and how nanoparticles and macroscopic objects interact with each other using these forces. But interestingly, number 3 is for molecules of appreciable size with medium dipole moments. Number 3 is actually the strongest one. So the London dispersion interaction arises from transient polarization of a nearby molecule by electrons, orbiting a nucleus in a perfectly circular manner, which we know that they all do, of course. Just kidding. Okay, so they all attract. Does that mean by convention, if the potential energy at infinite separation is high, and when they're close to each other it's low, that means that the interaction energy produces an attractive force is negative. So upon moving two objects closer together, the interaction energy is negative. So we're going to call these W, I, and J, which is the interaction energy which is negative because it's favorable. And I and J are two different molecules. There's the ith type of molecule and the jth type of molecule. So let's imagine a tic-tac-toe board full of closed circles, except for one. These two in adjacent sites interact by W11. We're going to say that there's no interaction between the diagonals, just to make our lives easier, and there's no interaction over ranges longer than one lattice site. So this is W equals 0. Similarly, for a tic-tac-toe board comprising open circles, no interaction energy here, and these two molecules interact by 2,2, W22. Now, if we mix two of these species together, we have W22 here, W11 here, and we have a cross term W12 here. Our total enthalpy, sorry, not our total enthalpy, our enthalpy of just the ones, enthalpy of the ones is 1/2 the number of ones times Z times W11, where Z is the number of neighbors. The 1/2 is to prevent overcounting, because these are pairwise interactions. You don't want to count the same one twice. And H2 is 1/2 N2 times Z times W22. So upon mixing, we need to include a term that describes the probability that an adjacent molecule is filled by one of the opposite type. So which is just x1 or x2, which is the mole fraction of 1 and the mole fraction of 2. So the probability of an adjacent site being occupied by 1 or 2 is x1 or x2. So our heat of our enthalpy of the mixed state is 1/2 N1 times the quantity Z x1 W11 plus Z x2 W12. So this is the number of molecules of 1 times the normal probability times the energy that it will be interacting with one of its own kind, plus another term which accounts for the fact that it could be next to one of the other type, and its interaction W12, which is the energy associated with two unlike molecules coming together, plus the 1/2 N2 Z x1 W12 plus Z x2 W22. If I write down here, can people not quite see maybe? All right, I'll move over here. Okay, so the change in enthalpy, delta H upon mixing, is the enthalpy of the mixed state minus the enthalpy of the pure components. So we have 1/2 times Z times the quantity W12 N1 x2 plus N2 x1 plus W11 N1 x1 minus N1 plus W22 N2 x2 minus N2, and we're going to skip some algebra, which is in the notes, to arrive at N1, N2 over N0 times Z times this exchange energy, W12 minus W11 divided by 2 minus W22 over 2 equals N1, N2 over N naught Z times delta W, where this whole thing is delta W. And this is the exchange energy. And for unequal intermolecular forces, it's greater than or equal to 0. So the potential energy of the system increases by having unequal intermolecular forces. Let's make our lives a little bit easier by defining an interaction parameter chi, which is sometimes called the Flory Huggins interaction parameter, where chi equals Z delta W over KT, and this is the exchange energy per molecule normalized by the thermal energy KT. Or that is the fraction of KT that must be paid in order to move a molecule of 1 into the environment of 2 and vice versa. The fraction of KT that must be paid to exchange molecules of 1 or 2 into each other's pure phase. So what we have for the total expression for HM in terms of chi is N1 X2 chi KT for the number of molecules, but we can swap between the number of molecules and the number of moles by saying little n1 x2 chi times RT, where we've made the substitution that the Boltzmann constant K is the universal gas constant R divided by Avogadro's number. And this is the number of moles. And this is for the whole system. Or we can express it on a per lattice site basis. This is per lattice site or molecule. And the consequence is that when the interaction parameter chi is greater than 0, delta H of mixing is greater than 0 and opposes spontaneous mixing. And if we use the Gibbs free energy equation, delta G equals delta H m minus T delta S m. We have a total expression delta G m over RT equals, this is the final result. This is the delta G of the regular solution is N1 natural log X1 plus N2 natural log X2 plus N1 X2 chi, and this is for the system in terms of moles. Or per molecule or per lattice site in our model, delta Gm over kT equals x1 natural log x1 plus x2 natural log x2 plus x1 x2 chi per molecule or lattice site. Okay, so we boiled this down to pretty much what we had last time, where we can make the appropriate substitutions for polymers in terms of big N's and phis from the Flory Huggins entropy, which we'll do at the beginning of class next time, plus this enthalpy term. This enthalpy term came as a result of the fact that exchanging 1 and 2 into each other's business gives you gives you a non-zero change in entropy because the intermolecular forces are different. So this is the combinatorial term. That is the favorable entropy of mixing. And this term is the contact dissimilarity. Or the unfavorable enthalpy of mixing. So the key result we will arrive at on Wednesday is the fact that if Component 2 is a polymer. We saw based on the Flory Huggins entropy of mixing, component 2 is a polymer. The entropy of mixing associated with 2 is very low for high molecular weights. And if we lose lots of this entropy, which is favorable, we're left with the unfavorable enthalpy of mixing, which encourages phase separation. Now, what if they were both polymers? Then the entropy of mixing would go to basically 0 with higher molecular weights, and the only thing we'd have left is the unfavorable enthalpy of mixing. So that's why two polymers don't want to mix together in general, although there are always exceptions. And of course, one of the ways to get around this is through block copolymers. But block copolymer phases still want to phase segregate, but when they do, they give us really useful, cool nanostructures that can be used to make microprocessors and filtration membranes and all the sorts of things that block copolymers do. So what we're going to do next time is plot the delta H of mixing, the delta S of mixing, delta G of mixing, and then construct phase diagrams that give us at least qualitatively where, as a function of temperature, we can expect one-phase behavior, two-phase behavior, and the presence of mixed phases. So thanks for bearing with me through today. I will see you on Wednesday.